Hello, good morning all. Today we are going to discuss some of the questions that we have already discussed, some of the topics that we've already discussed. We will enter into a new field in linear algebra, which is called as the linear transformation. Please note that this is an important topic from where the questions have appeared in the exam. Okay, linear transformation is one of the topics, and also understand that before we start with linear transformation, I want you to just revise your concepts. So as you are aware that we've already done subspaces and a few concepts like bases, dimensions, linear independence, and dependence. And today I want to through some of the questions on subspaces so that you are well aware with the concept, and then we'll move forward very quickly. Okay, so today I'm going to do a few questions so that you get a understanding of all these topics all over again, and then we'll move. I hope vector spaces everybody knows. Okay, so vector spaces I have discussed in detail. I have discussed all the properties in detail. I have proven many of the sets a vector space already. Now today in this lecture I'm going to do a few questions on subspaces, and then I'm going to move on basis, dimensions, doing some of the questions so that your concepts become very strengthened in these topics, and then we'll move to linear transformations. Okay, so the question says that the question number one states that, do you think that this particular thing, okay, let me just give me a minute, this grammarly thing is okay. So do you think that this particular space that is given by x1 x belongs to R cube? This is a please do remember this is a vector. Okay, so this x would contain this. So x would contain this. Okay, and such that x1 minus 4x2 plus 5x3 equal to 2. So do you think it will form a subspace? The answer would be no. Why? Because you know that the zero vector, or you can say the additive identity, the additive identity or you can say the additive identity of R cube is what? The additive identity of R cube is 0 comma 0 comma 0. And do you think that this additive identity would be contained in S? No, indeed no. Do you think 0 comma 0 comma 0 would be contained in S? Would be contained in S? Answer is no. Clearly you can see that 0 minus 4 times 0 sorry, and plus 5 times 0 will never be equals to 2. So clearly the zero vector of this main space, that is R cube, the zero vector, or you can say what you say additive identity of R cube is not contained in S. So therefore you can say that S does not form a subspace. So S does not form a subspace. I hope it is clear. Now let us move to another question, and the question says that, do you think that this forms a vector, subspace? So example I'm giving you, let us say it is as S2, and let's say x belongs to R square such that y is equal to x square. Do you think this forms a subspace? So let us take two examples. Okay, so consider two examples. Okay, so consider two elements, let's say 1 and 1, and take minus 1 and 1. Okay, so both of them will be contained in S2, isn't it? Both of them would be contained in S2. So clearly, if you do the square of x, you are going to get 1. If you do the square of x, you are going to get 1. So clearly, x is square equal to y. So therefore, these two vectors would be contained in x2. Remember, if you have to prove that W is a subspace, then you take what? You take two elements, W1 and W2 belongs to W, and you see that whether W1 plus W2 also belongs to W, right? So let us do that. Let us say this is your x1 and let's say this is your x2. Now let us consider the sum. So the sum would be x1 plus x2, which will be equals to what? It would be equals to 0 comma 2. Clearly 0 square is not equal to 2. So it is not, so it does not belongs to what? S2. So therefore we can say that S2 is not a subspace. I hope it is clear. Is that clear? Okay, now let us take another example, S3. If you remember, I have already mentioned that the set of polynomials with real coefficient, form a vector space, and that set is given by P. If I write Pn, what does it mean? It means set of polynomials with degree at most n. So Pn implies what? It implies that set of polynomials with degree at most n. Okay, with degrees at most n. So what do I want to say? I want to say that let's say this is your example. Fx belongs to P4 such that f1 is an integer. Do you think this S3 forms a vector space? Sorry, subspace. Does it form a subspace? So what does P4 represent? P4 represent set of polynomials with degree at most 4. Degree at most means what? You can have degree 4 or less than 4. So let us take one simple example to negate this. So let's say take example fx equal to x. You know that f1 would be equals to clearly you know that degree is 1 and degree 1 is less than 4, right? So what would be f1? F1 would be 1 and clearly it will belong to S4, right? Because 1 is what? Integer. So it will belong to S4. Now take any scalar. Let's say alpha belongs to F. We want to take a field element and that field element, let us take it as 1. Now clearly, if I do alpha into F1, what it would be? It would be simply equals to 1 upon 2 into F1, which is equals to 1 by 2. And 1 by 2 does not belongs to S4. So clearly, the second case is violated. Remember, whenever we have to prove, that something is subspace, one of the things is you can do this, or another thing is that you can do this. You can prove that if W1 and W2 belongs to W, then alpha W1 plus beta W2 should belong to W. And third thing, you see, you can do one more thing. You can take some element alpha and try to see that whether alpha W also belongs to W. So if this and this is satisfied, then we say that it is a subspace. If one of them is violated, then we'll say that it is not a subspace. So clearly S4 is not a subspace. I think it was S4 or something. S3, sorry. S3. Okay. So clearly S3 is not a subspace. Okay, now let us move to another example. I'm just taking some examples so that the concepts get revised and then I'll move forward. Okay, let us take another example. Let's say S4. S4 represents all those functions belongs to P4 such that F1 is a rational number. Is a rational number. Do you think this forms a subspace? Indeed, no. Why? You can say that. Let's say again take example. Let us take example fx equal to x. Clearly, it will belong to P4, and we know that P4 is what? Set of polynomials with degree less than equal to 4. So clearly, the degree is less than 4, and we also know that the P that is the set of all polynomials with real coefficients form a vector space. Now consider the scalar alpha equals to root over 2. And what would be f1? F1 would be simply 1. If f1 is 1, then alpha f1 should also belong to S4 in case it is a subspace. But what is alpha f4? Alpha f1. What is alpha f1? It is equal to root 2 times 1, and clearly it does not belongs to S4. So therefore, I can say that it implies that S4 is not a subspace. I hope it is clear. Please keep uh, pushing the answers so that at least you keep commenting so that I'll be able to understand that you're getting it. Okay, so today I'm going to go a little bit fast and I'm going to cover much of the topics via problems so that you're able to strengthen your hold on this particular subject. Okay. So consider another example. What should I take example as? S5. Consider that A belongs to set of matrices, 2 cross 2 matrices. Let's say with real entries, if you want to take with real entries, and we want to say that determinant of A is not equal to 0. Do you think that this forms a subspace? Do you think this forms a subspace? Okay. Do you think this forms a subspace? No, indeed no. See why? Let us take example. Okay, so we know that this is something that I will prove today also. But also remember, see, what is a 2 cross 2 matrix? 2 cross 2 matrix is after all this. Now, whether I write this or whether I write this, it's after all way of representing things, right? So you can say that this matrix can be related as R2 square, that is R4. And we know that the Rn forms a vector space over R. However, I can give a derivation to this also, but just understand, just relate this matrix to this. Okay, just relate this matrix to this, and you know that Rn forms a vector space here. Since Rn forms a vector space, so clearly this would also form a vector space. So always remember that set of set of matrices with real entries n cross n always forms a vector space. However, I'm going to probably prove it today or tomorrow. Yes, if I want to prove. So it forms a vector space. Now it says that whether this forms a subspace or not. So it indeed does not form a subspace, because see, always remember the zero matrix is belonging to this. Zero matrix belongs to this, and this will be an additive thing, because see, if you take a 2 cross 2 matrix, let us say A, B, C, D, and if you add 0 0 0 0, only then you will get A, B, C, D, right? So what does it imply? It implies that your this A, B, 0 0 0 0, this is your additive identity. And according to the rules of subspaces, the additive identity of the main vector space, that is a parent vector space, should be contained in this S5 also. But do you think that 0 0 0 would be contained in S5? No, because we know that the determinant for this would be 0. So it implies what? It implies S5 is not a subspace. S5 is not a subspace. Okay, now take another example. S6. Do you think this forms a subspace? If I take, let's say A belongs to such that so answer is no. Why? See, I'll take two examples, 1 0 0 0, and another example I'll take 0 1 0 0. Clearly the determinant is 0 for both of these matrices. Let's say this is your matrix A, this is your matrix B, and both A and B belongs to S6, right? Now if they qualify the definition for subspaces, then their sum should also belong to S6. Now let us take their sum. Sum is what? Not 1 here, take 1 here. Okay, now take sum would be 1 0 0 and 1. Clearly the determinant of A plus B would be 1. Certainly not 0. It implies what? It certainly does not belongs to S6. It implies that S6 is not a subspace. Is not a subspace. Okay, now do you think this forms a subspace? Okay, now always remember, I'm writing it here. Set of continuous functions form a linear vector space. So set of continuous functions always form a linear vector space. Okay. Now you see the class of functions, class of continuous functions. Class of continuous functions on a comma b is denoted by c a comma b. So if I'm writing this, it implies I'm talking about continuous functions on the interval a comma b, closed interval a comma b. So let us take another last example. Do you think that these functions which satisfy this is like c on minus 2 comma 2 such that f minus 1 and f1 is equal to 0? Do you think that this S7 is a subspace? Do you think this is a subspace? Do you think this is a subspace? No. A subspace cannot have. Subspace cannot exist without a zero element. So somebody has asked a question. See, subspace is a vector space in itself. Okay, subspace is after all a vector space in itself. So for a vector space to exist, you should have an additive identity. If it does not have an additive identity contained, then it will be not a subspace. You cannot understand the point. Subspace is after all a vector space in its own right. That is what I want to convey. So if that's the case, do understand that a subspace should have an additive identity. So the additional thing is that the zero element of the parent space of which it's the subspace, the zero element of the vector space should be contained in the subspace itself. Bharat, is that clear? Or not clear? Okay, so remember this. Okay, now see, this is the example. Now let me negate it. So today, whatever I've done, I have yesterday, day before yesterday, when I was teaching subspaces, I was doing some questions regarding proving subspaces. Today, I'm giving you some counter example to negate subspaces. Okay, so these are examples which would negate that the following is a subspace or not. So see, I've already told you that this C on minus 2 comma 2, what does it represent? It represents class of continuous functions. It represents class of continuous functions on what you can say on minus 2 comma 2. It represents class of continuous functions on minus 2 comma 2, right? Also understand that linear function in general, linear function forms a is a continuous function. So let us take two functions. Let us say fx and another one is gx. If I'm saying that this forms a subspace, S7 forms a subspace, what does that mean? If I take, let's say, fx belongs to S7, which indeed is the case. See, if I take fx is equal to x minus 1, clearly f minus 1 into f1 is equal to 0, right? See, you just take 1 here, so 1 minus 1 would be 0. F minus 1 would be minus 2. So clearly minus 2 into 0 is 0. So fx indeed belongs to S7, and you can also verify that gx also belongs to S7. But do you think that sum would belong to S7? So the fx plus gx is what? It is equals to h of x, let's say. And what is h of x? H of x would be simply twice x. And now let us do f minus 1 and f1. It would be equals to what? It would be equals to minus 2 into 2, which is equals to 4, and which is certainly not equal to 0. So clearly it does not belongs to S7 set. So you can say that S7 is not a subspace. is not a subspace. Let us take one last example and conclude this discussion of subspaces in general. Let us take another example. Let's say S8, um, which is given by fx belongs to C minus 1 comma 1, fx greater than equal to 0 for all x belongs to minus 1 comma 1. Do you think this forms a subspace? Do you think this, oh sorry, this forms a subspace? Do you think this forms a subspace? Indeed, no. See why no? For this, just take one example I'm taking. So class of continuous functions on minus 1 comma 1. Don't you think that fx equal to x square is a continuous function? Clearly it is. Okay, fx equal to x square is clearly a continuous function. It is clearly a continuous function. Since it is clearly a continuous function, I can say that, and further I can also say that fx is greater than equal to 0, right? Now uh, just think of f1. F1 would be what? F1 1 square. Clearly it is also greater than equal to 0. It will be there in S8. Now if there is an element in S8, then its scalar multiplication should also belong to S8. If it is a vector, if S8 is a subspace, if S8 is a subspace, then the scalar multiplication alpha S8 should also belong to then alpha fx should also belong to what? S8, provided fx belongs to S8. S8, no, right? But take alpha is equal to minus 1. If I take minus 1, so minus 1 into x square, clearly it is less than 0. Or you can say f1, no? F1 would be what? Less than 0. So clearly alpha times f1 is not contained in S8. We can say that S8 is not a subspace. Is that clear to everyone? Okay, so yesterday we were doing something called a span, if you remember. Okay, span. And just to recollect what was span. So what is a span? Span is the all possible linear combinations. Span is all possible linear combinations. So for example, I will just write what was span. So if V is a vector space over field F, if V is a vector space over field F, and S is a subset of V, then the linear span of S, which is denoted by S, this is nothing but it is equal to set of all linear combinations. Set of all linear combinations. Let us say I took also one of the examples. Okay, and one of the theorems in linear algebra, which I'm not going to derive, suggests that if S is a subspace, then S is equal to this entire linear span. If only if S is a subspace. So just a point to note. Okay, however, it's not that important for you all, but just a point to note that if S is a subspace of V, then the linear span of S is equals to S itself. So okay, now what is a linear set of all linear combinations? So probably I've done a few examples to illustrate this. So I've taken example of 0 comma 1 and 1 comma 0. Clearly they both belong to R square. They both belong to R square. Is that clear? Yes or no? Okay, let us say that this is your set. This is a set 0 comma 1 and 1 comma 0. Clearly this set is a subset of R square, right? What would be the linear span of S? Linear span of S would be complete R square. Why complete R square? What is linear combination? What linear combination you can make out of these two vectors? It will be alpha 0, 1 plus beta 1, 0. Here alpha and beta both belongs to R. So if I take the linear combination of these two vectors, that is 0, 1 and 1, 0, what am I going to get? I am going to get beta, alpha. And clearly this is real, all the real numbers can be here, all the real numbers can be here. So what it will make? It will make your entire Cartesian plane. So you can say that the span of S would be complete R square, will be complete Cartesian plane. Will be complete Cartesian plane. Is that clear? So this is how you form the span. So from 0, 1 and 1, 0, from these linear combinations, you can write any plane vector in the space, not in the space, any plane vector on the Cartesian plane, any plane vector on the Cartesian plane. So you just take. Otherwise, if you have a little bit of understanding, what is 1, 0? It is I cap only. What is 0, 1? It is j cap only. So if you want to relate it to standard 12th notations, so I 1, 0, the teachers used to say that this is the directional cosine corresponding to x-axis 1, 0, 0. Okay, so if I reduce it to 2 dimensions, then it is 1, 0 would be what? 1, 0 would be simply x-axis. 0, 1 is what? It is simply y-axis. So in I cap and j cap, you can span the entire R square, or you can say that from this you can generate entire R square. And in fact, I've told you that these forms the standard basis vectors. The standard basis. Okay, so I told you yesterday that for Rn, the standard basis would be what? So if you remember, for Rn, okay, and remember that Rn over R forms a vector space. Okay, remember this. So for this particular thing, you have standard basis, that is E1 cap is equal to 1, 0, 0 dash 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 0, and so you can go on and write En cap would be what? It would be 0, 0 dash 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 1. I hope it is clear. Okay, so let us do a few questions on this particular concept, and then we'll move further, because probably many people have joined today, so that's why I'm saying. So let us do a few questions on this Rn over R. Okay, just remember, these are the standard basis. These are called as standard basis. Okay, and also I told you that it's not necessary that only these will form a standard basis. For example, yesterday I took one of the examples and explained that, let's say if you have 1, 0 and you have a 0, 1, people have an understanding that these are only two. Like, everybody thinks that basis vectors are unique. No, basis is not unique in general. Why it is not unique? You want to span the entire R square. You want to span the entire R square. Here is my suggestion: take 1, 1 and take 1, minus 1, and still you can do this. Do the same. Still you can do the same. Say you want to span entire R square, means you want to see that any point of alpha, beta type, okay, which is so here alpha is any arbitrary R, beta is any arbitrary R. So by this you can span entire space, right? But after all, any point in R square can be written as alpha, beta only. No? You take any real number here, you take any real number here. So by taking any real number, can you not span the entire space? Entire plane. Is that clear? So do you need always this vectors 1, 0 and 0, 1? No doubt these are standard ones, but they are not unique. You can do the same using this also. Just take this alpha plus beta. You take alpha plus beta by 2, 1, 1, plus take alpha minus beta by 2, 1, minus 1. So in this way you can express your alpha, beta. In this way you can express alpha, beta. So any vector alpha, beta, or any point alpha, beta can be expressed as the linear combination of 1, 1 and 1, minus 1. I would say that these two also can generate entire R square. They can also generate R square. Is that clear? Please let me know. So this is something that you should keep in mind, that it's not necessary that only these standard basis ones are standard bases are going to span the entire space. Even these can. I hope it is clear. If that's the case, then I'll move further. Just let me know that whether these, what do you think about them? Is that clear or not clear? I don't know. Okay, chalo. I'll give you a question and I'll understand that whether you're getting it or not. So let's say if S is equal to 1 comma 2 comma 1 and another one is 2 comma 1 comma 0. Indeed, in these two elements, after all, are subset of R cube, right? It is a subset of R cube. We want to determine whether the following vectors of R cube are in S, are in linear span of S, sorry. Okay, so option number 1 is 5 comma 3 comma 1. Option number B is 2 comma 1 comma 0, and option number C is 4 comma 5 comma 2. See, I'll do this question for you. The next question I'm going to give it as an exercise right now. Try to do it. Okay, right now this question I'm doing it for you. Don't worry. See, understand that these two are 1 comma 2 comma 1 and 2 comma 1 comma 0 belongs to R cube. This is quite clear. This is quite clear. These are after all like triplets, or you can say 3 tuples are given to you. Understand that what is S? Again, I'm saying what is S? S is the set of, like this. What is linear span of S? Linear span of S is a set of all linear combinations of S. Okay, so let us take alpha belongs to R and let us take beta belongs to R and try to write the linear combinations. So linear combination would be what? Alpha times 1 comma 2 comma 0 plus beta times 2 comma 1 comma 0. So what would be linear combination? It would be alpha plus 2 beta here. Then you will have 2 alpha plus beta, and then you have simply alpha. Okay, so now in order to understand that whether these elements 5 comma 3 comma 1, 2 comma 1 comma 0, 4 comma 5 comma 2 belongs to a linear span, what you need to do? You need to check. So let us check that whether alpha plus 2 beta, 2 alpha plus beta and beta, can this be equals to 5 comma 3 comma 1? Because if 5 comma 3 comma 1 lies in the linear span of S, then it should comply this. It should comply this equality, isn't it? It should comply this equality. Yes or no? I guess this is clear to you. And if at all it complies this, like if it complies this equality, then I would say that alpha plus 2 beta should be equals to 5, 2 alpha plus beta should be equals to 3, and then beta should be equal to 1. If beta is equal to 1, clearly I can say that my alpha would be equals to 2. Not even 2, it would be 1. It would be 1, sorry. It would be 1. Okay, it would be 1. It would be 1 because beta, if I write here beta is equal to 3 minus 1 is 2, 2 alpha is equal to 1. If alpha is equal to 1, if I place 1 here, beta is equal to 2. If I beta is equal to 1, if I place here, clearly this will never be equals to 5. If alpha is 1, then 2 beta will be equals to 2. If you add them up, it will never be 5. So clearly I can say that 5 comma 3 comma 1 is not contained in the, or you can say is not contained in, or does not belong to the linear span of S. Is that clear? Understand what is linear span. Again, I'm saying linear span is nothing. If you are given a set S, which is a subset of a vector space, So R cube forms a vector space. This is clear. I have already done in the first lecture itself that Rn over Rn forms a vector space over R. Always remember. So R cube will always form a vector space. Don't worry about it. So S is a subset of R cube. That was clear. What is linear span of S? Linear span of S will comprise of all the possible linear combinations from that elements of the set. So from elements of the set, all the possible linear combination would be equals to what? Alpha times 1 comma 2 comma 1 and beta times 2 comma 1 comma 0. Okay, and if you do the same, and if 5 comma 3 comma 1 happens to be in the linear span, then this equality should follow. And if this equality follows, then you can clearly know that they are not simultaneously satisfied. If beta is 1, then alpha would be 1, but and alpha plus 2 beta will not be 5, right? Alpha plus 2 beta would be then 3. Okay, now what do you think 2 comma 1 comma 0? So 2 comma 1 comma 0, do you think that this belongs to set S, linear span of S? Does this belongs to linear span of S? So again the same thing, you have to see that whether alpha plus 2 beta is equal to 2, 2 alpha plus beta is equal to 1 and beta is equal to 0. So if beta is equal to 0, then it implies that alpha would be equals to what? Half. If alpha is half, beta is 0, then alpha plus 2 beta can never be equals to 2. So clearly again, this 2 comma 1 comma 0 is also not contained in the span S. Span of S. I hope it is clear. And similarly, if you want to verify yourself 4 comma 5 comma 2, again the same process will go on. And you have to see that whether 4 comma 5 comma 2 belongs to set. Okay, 2 comma 1 comma 0 belongs. 1 minute, let me see. Have I done some mistake or what? 2 comma 1 comma 0 no, so alpha was half. कैसे हो सकता है? 2 comma 1 comma 0 cannot belong to S, है ना? So 2 comma 1 comma 0, how can that belong to? Say 2 comma 1 comma 0 to belong, then beta should be equal to what? 0. Is that right now? एक बार देखें ध्यान से. Okay, what is that? I mean 2 comma that was very much clear now. So okay, yes, indeed it belongs. 2 comma 1 comma 0, indeed it belongs. See, 2 comma 1 comma 0 is there itself in S. So you just take alpha to be 0 and take beta to be equal to 1. Sorry, my mistake. You just take alpha is equal to 0 and beta equal to 1. Okay, 2 comma 1 comma 0 indeed belongs to span S. Because 2 comma 1 comma 0 is already contained. I think there is some calculation error we have done. So it indeed belongs there. Because see, 2 comma 1 comma 0 already belongs to set S now. See, here it is. It already belongs to set S. Just see. Since it already belongs to set S, the best way is take alpha is equal to 0 and take beta is equal to 1. And your things will be done. You'll get, because if you take alpha to be non-zero, then it will never be there in the linear span of S. It does belong. Siddhi, it does belong. Sorry, my mistake. See, understand the point. Again, I'm referring it here. See what we were doing. Just give me a minute here. Okay. So what we were doing. Okay. So if 2 comma 1 comma 0. See, 2 comma 1 comma 0 belongs to set S, right? It belongs to set S. Then it will always be contained in this thing, linear span of S. Because after all, what is linear span? Linear span is all possible linear combinations now. So we can say that S is always contained in this. So here just don't do this alpha plus beta, otherwise you will get confused, because alpha and beta are both non-zero here. So if I take beta to be 0 here, then things will become difficult for you. See, again I'm explaining. See, S was what? S was, I think, 1 comma, what was that? S was 1 comma 2 comma 1 and this was 2 comma 1 comma 0, right? If this is the case, just think that this S is already there. Okay, I understand. See, I understand you must be taking alpha 1 comma 2 comma 1 and beta 2 comma 1 comma 0, okay, in order to generate 2 comma 1 comma 0, right? Is that clear? If you want to generate this 2 comma 1 comma 0, can a simple solution not be there that just take alpha equal to 0 and beta equal to 1? It can be there, no? After it represents all the possible linear combinations. Can that not be done? It can also be done. If this can be done, then clearly if beta is 1, then it is equals to this. Is that clear or not? Okay, if we take alpha to be non-zero, then what happens? Then it will result to this kind of thing. Okay, then this will result to, okay, there is a mistake here. This is 1 comma 2 comma 1, right? The first one was that, therefore we did the mistake in initial case also, implies 1. Okay, see, I think I made somewhere. Okay, there it is. Here is a mistake. So alpha plus beta. So if I write, okay, there was a mistake here. So alpha plus beta is equal to 1. If alpha plus beta equal to 1, then try to solve this also. I think there is a mistake in the first one also there. So alpha plus beta equal to 1. 2 alpha plus beta is equal to 3. To try to solve from here. So try to solve from here. We will get 2 alpha plus beta is equal to 3 and alpha plus beta is equal to 1. Subtract them. So you are getting alpha is equal to what? 2. So you are getting alpha is equal to 2. Sorry. So you are getting alpha is equal to 2 in the first case. Okay. And if alpha is equal to 2, then beta would be equal to minus of 1. Oh, there's a mistake here. So beta would be what? Beta would be equal to minus of 1 in the first case. So if alpha is equal to 2, sorry, boy. So last term is alpha. Right. My mistake. See what I did actually. This is 1 comma 2 comma 1. This is 2 comma 1 comma 0. So if you add this now, so this would be, acha, this is alpha, right? This is only alpha because 0 will not be here. So this will not be here. So alpha would be 1. Okay, let us do it all over again. I think I have messed it up completely. Just give me a minute. Okay, so we'll redo it. Okay, we'll redo it. Don't worry. So we'll redo it so that abhi confusion hai, it will be cleared. Okay, it will be cleared. Just give me a minute. Okay, just give me a minute. Therefore, such careless mistake I should not do, but okay. Okay. Let us do it all over again. My mistake. Okay. That is, I was saying what's happening. Okay, so see now let us do it all over again. Okay, now let us take alpha and beta again, and see this is easier one. Okay, so this is, let's say, alpha. Okay, my mistake. Okay, let me correct it all over again. Okay, so alpha is this, and we wanted 1 comma 2 comma 1 here, and we wanted beta 2 comma 1 comma 0 here. Okay, and we wanted to see whether it forms 5 comma 3 comma 1. We want to see that whether 5 comma 3 comma 1 belongs to the span of S, right? This is what we want to see. So this will be like alpha plus 2 beta comma 2 alpha plus beta, and then yes, Siddhi was right indeed. So it was alpha here. Okay, I wrote beta here, so there was a confusion. So this will be 5 comma 3 comma 1 here. Now let us compare. This will give me alpha plus 2 beta is equal to 5, 2 alpha plus beta is equal to 3, and alpha is equal to 1. If alpha is equal to 1, then beta would be equal to what? 1. Surprisingly, the answers are again the same. If alpha is equal to 1, then beta would be 1, because see, if alpha I am writing it as 1, then beta would be simply 1. Alpha is 1 and beta is 1, then alpha plus 2 beta can never be equals to 5. It will always be equal to 3. So clearly 5 comma 3 comma 1 is not contained in the linear span of S. Now let us take the another example. See, that is very much clear also. See, if S is equal to 2 comma 1 comma 0, indeed you can take alpha is equal to 0 and beta is equal to 1. And also see that after all, what is linear span? Linear span is all possible linear combinations of S only. Na? So one of the linear combination can be this itself, and another one can be simply taking alpha equal to 1 and beta equal to 0. Is that clear? And this we can verify also. This we can verify. Probably that is a mistake that we were doing. That is why we could not verify it. Is that clear? Not clear? Siddhi, is that clear? I mean, एक मिनट देखते हैं. Let us see. So what was the thing? Just let me help myself here little bit. Okay, so this is 1, this is 2, and this is it. Okay, so what was the term? Alpha 1 comma 2 comma 1, and then you have this beta 2 comma 1 comma 0, and you have to see whether it forms 2 comma 1 comma 0 or not. So if that's the case, alpha is equal to 0 clearly. If you see from here, this the last tuple is 0, so it implies alpha is equal to 0. That implies what? That implies beta 2 comma 1 comma 0 is equal to 2 comma 1 comma 0. Yes. So sorry for the mistake. Okay, so now beta is equal to 1. Okay, so actually I messed it up while doing it very fast. Okay, so that is something that you should also remember for exam. Just don't hurry, otherwise such simple question can be messed up even. So okay, and now just verify whether 4 comma 5 comma 2 is there in linear span of S. Just confirm that 4 comma 5 comma 2 belongs to linear span of S. Okay, so 4 comma 5 comma 2, for that to be there you can write that alpha plus 2 b, sorry, what was that, alpha plus 2 beta should be equals to 4. What was that, then 2 alpha plus beta should be equals to 5, and uh, alpha should be equals to what, 2. Simply alpha should be equal to 2. If alpha is 2, then beta would be equals to 1, and if beta is 1, then clearly you can see that alpha plus 2 beta is equal to 4. So we can say that 4 comma 5 comma 2 belongs to set the linear span of S. It indeed belongs to linear span of S. I hope it is clear. Now let us do another question, and now I'll leave it for you to do it, and I'm giving you a minute or so to think about it, and then we'll proceed. The question says that let P be this, let P be the vector space of polynomials over R, and over R means with real coefficients, okay, and S, this S is a subset which gives you x square plus 1, and I'll write x cube minus 1. Okay, I'll write x cube minus 1. Now what I'm asking to you is determine that the following polynomials, determine that the following polynomials are in S. So let us see, the polynomial number 1 I'm saying is x square plus x plus 1, and second one is simply 2x cube plus x square plus 3x plus 2. Now think about this. You have to do this question, and I'm giving you a minute or so, and then I'll do this for you. Okay, so I guess I have given enough time. I'm giving you a minute or so. Try to do this. Okay, so let us do this. Okay, so what it would be? So option number A that is given to you is this thing. So let me do it for you. If you can write this thing, this what would be the linear? Okay, what are the linear span? Okay, this is linear span. Okay, so what is the linear span of S? So you can write the linear span of S would be equals to what? You just write it as some alpha, beta, gamma. You can take, okay, if you want. You can take ABC as well. Okay, so if you take ABC, so then it would be what? It would be simply, okay, so this will be simply A times X plus B times X square plus B plus C times X cube minus 1. Okay, so this will be this is how you can write your linear span of S. So linear span of S would be, I think, CX cube plus BX square plus AX plus B minus C, right? Okay, so this is how you can write. Now if you are saying that this belongs to linear span, then it implies what? That it implies that C should be equal to 0, right? C should be equal to 0, B should be equal to what? 1, if because cube term is not here, and B should be equal to 1 because X square is here 1, and A should be 1, and if A is 1, okay, and this is B minus C, right? If A is 1 and C is 0, so clearly we can see that X square plus X plus 1 belongs to the linear span of S. Yes or no? Please let me know in the comment section. Is that clear to you? Okay, and whether the second term belongs to this or not, for that I'll have to see. Okay, just give me a minute. Okay, so for the second term, second one was what? It was 2x cube, so I'll write cx cube plus bx square plus ax plus b minus c should be equal to what? It should be 2x cube plus x square plus 3x and plus 2. So from here c should be equal to 2 and b should be equal to what? 2. If c and b are both 2, then b minus c should be equal to what? It should be equal to 0, and however from here we know that b minus c should be equal to 2. It implies what? It implies that 2x cube plus x square plus 3x plus 2 is not contained in the linear span of S. I hope it is clear. Okay, so this is all what we can do for the span. This is all we can do for the span. Now let us do a few questions on linear dependence and independence. Linear dependence and independence. Okay, now let us check a few questions for the linear dependence and independence. I told you yesterday that a set, I told you that if V forms a vector space over field F and V1, V2, V3, these are all vectors in vectors belonging to set V, and there are some scalars alpha 1, alpha 2, dash 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 alpha n, then we say that this set, what I can say, this set V1, comma V2, comma V3, dash 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 Vn forms a set of linearly independent vectors. It forms a set of linearly independent vectors when alpha 1 v1 plus alpha 2 v2 dash 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 alpha and bn gives 0, is 0, implies alpha 1, alpha 2 and all are equal to 0. Okay, and if they are linearly dependent, so let's say, again I am giving you an example. Let's say not take this example, let us take two examples. Like if I'm saying that these are linearly dependent, what does dependent means? It means I can express my v1 as minus alpha 2 upon alpha times v2. That is, if I can express my vector 1 in form of another vector, then I can say that these are linearly dependent one, and for this to have, alpha 2 must be non-zero and alpha 1. So clearly, from here we can say that not all can be zero, not all can be zero. So I can say, if I'm saying that summation alpha I vi is equal to 0, and it implies that alpha I is a not 0, then I would say that my set v1 v2 dash 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 vn form a linearly dependent set. Is that clear or not clear? Please let me know. Okay, so at least some AI should be in such a way that they are non-zero. Okay, for linearly independent ones, all of the AIs should be zero. Is that clear? I hope everybody is following it or not following it. Please let me know. I think a few of them are still there in the class, so I'll wait for the response and then I'll go further. Please let me know if that this is something that you know. I mean, this is something I've already taught, but just give me a feedback that you are there or not. Is that clear? Okay, good. Chalo. So let us go a little bit further in this one. Let us do a few more questions for this. Okay. So if okay, good. So okay, so this is something that we have already done. Now let us verify it for a few simple cases, and then we'll go a little bit. We'll try a little bit difficult ones also. Okay. Okay, and please mind you, this is an important concept with your quantum mechanics also. So you have to pay attention here. Although it seems very easy, but still that is why I'm doing it, because again, in quantum mechanics, after all, eigenfunctions, you're going to write all these things all over again. Linearly independent set of eigenfunctions and everything of this sort. Okay, so just check. Okay, just check which of the following forms, which of the following subsets forms linearly independent set of vectors in R cube. Okay, so let us say option number A is given to you 1 comma 2 comma 3, and this is just an exercise for you. Just do it very fastly. 2 comma 3 comma 1, and this 3 comma 1 comma 2. Then option number B given to you is 1 comma 2 comma 3 comma 2 comma 3 comma 1, and obviously there this is 2 comma 3 comma 1, and then you have minus 3 comma minus 4 comma 1. Option number C is minus 2 comma 7 comma 0, 4 comma 17 comma 2, and you have 5 comma minus 2 comma 1. And option number D is minus 2 comma, okay, leave this, leave this, it's enough. I think this, if you do, it would be more than sufficient. Okay. Okay. Which of the following, these are the three subsets I have given ABC. Just try to figure out that which of the following forms a linearly independent set of vectors. An independent set of vectors. Just try to find that. Okay, the first one. So if I write first one, this will be alpha a 1 comma 2 comma 3 plus b 2 comma 3 comma 1 and plus c 3 comma 1 comma 2. If I get a trivial solution, that is a is equal to b is equal to c. If I get a right. Exactly. Whichever way it suits you. See, I'll give you one other thing also. So see, a comma b comma c. If you get a trivial solution equal to 0, then I will say what? Then I will say that these vectors 1 comma 2 comma 3, 2 comma 3 comma 1, and 3 comma 1 comma 2 forms what? They will. If this is the case, if I write this equal to 0, okay. If I write this equal to 0, and I get a comma a equal to b equal to c equal to 0, then I can say that this forms then this 1 comma 2 comma 3 2 comma 3 comma 1 and 3 comma 1 comma 2 forms a linearly independent set of vectors. So what am I getting? I'm getting 1 plus 2b, I think, plus 3c here equal to 0. Another equation would be, I think, 2a plus 3b plus c equal to 0. And see, if I'm getting 3a plus b plus 2c equal to 0, right? This is my equation number 1, this is my equation number 2, and it is my equation number 3. Okay, if this is the case, then please do remember what I'm going to get. What I can do, I can add these two up. I can add these two up and subtract 3 from it, right? I can add 1 and 2 and subtract, whichever way it suits you. I think it will be, if I add them up and subtract, so this will be 4b plus, I think this will be 3c 2c equal to 0. So it will give me c should be equals to minus of 2b, right? This is 1. And if I place this up, so if I place this up, what I'll get a minus of 4b equal to 0. It implies a should be equals to 4b. From here, a is equal to 4b. And the equation number 2 will then give me what? A is equal to 4b. So I'll place 4b here. It will give me 8b plus 3b minus 2b equal to 0. It implies b is equal to 0. If b is equal to 0, implies c equal to. Okay, is that clear or not clear? Okay, so we can say that these set of vectors, which is 1 comma 2 comma 3, 2 comma 3 comma 1, and 3 comma 1 comma 2, 3 comma 1 comma 2 are linearly independent to each other. 1 comma 2 comma 3, 2 comma 3 comma 1, and 3 comma 1 comma 2 are linearly independent. Since this alpha times this plus b times this plus c times this equal to 0 has given us what? Has given us a equal to b equal to c equal to 0. Okay, now just think about the second one. What was the second one? It was, I think, 1 comma 2 comma 3, 2 comma 3 comma 1, and minus 3 comma 4 comma 1. So I'll do it. I'll write it here. It will give me a 1 comma 2 comma 3 plus b 2 comma 3 comma 1, and then plus c equals to c times minus 3 comma minus 4 comma 1 is equal to 0 comma 0 comma 0. Okay, now if this is the case, then what I'll get a plus 2b minus 3 equal to 0, minus 3c equal to 0. The other one would be 2a plus 3b minus 4c equal to 0, and then I can write 3a plus b plus c equal to 0. Try to do this. I think what I can do, I can subtract, then probably I'll get something from here. If I subtract and then add, okay. I think if I subtract this 2, so if I subtract 1 minus 2, what I will get? I will simply get a minus b, right? And I think plus c is equal to 0. This is another one, and this is 3a plus b plus c equal to 0. 3a, okay, and if I subtract them up, so I'll get minus of 4a minus of 2b is equal to 0. It implies 2b is equal to minus of 4a, so b is equal to minus of 2a. If b is minus 2a, if I write b is equal to minus 2a here, what I'm going to get? I'm going to get a plus c is equal to 0, it implies A is equal to minus of C, right? A is equal to minus C. So if A is minus C, 2B is, okay, A is minus C, and B is then, if I write A is equal to minus C, then I can write B is equal to 2C. So I'll get B is equal to 2C. What is that? I have made some mistake again. See, I'll do one thing. It's better to solve it separately. Otherwise, there would be some mistake that would be left. Okay, so you just extract these things okay, just try to extract the values ABC from these three equations. Okay, try to extract the values from these three equations. What I can do, इससे अच्छा तो एक काम करते हो, 3a right, ये गलत तो लिख दे, 3a plus b plus c is fine, 2a plus 3b minus 4c is fine, a plus 2b minus 3c is fine. ठीक है, now let us do. Okay, just give me a minute, no? Just give me a minute. Okay, B and C are not linearly dependent. See, right? Exactly. So how to verify that? I mean, I'm just trying to equate things up. So 3B minus 4C equal to 0. This is 1. And then you have A plus 2B minus 3C is equal to this. So what I can do, I can multiply it with 2, right? So I can multiply it with 2. This would be 4B. This would be minus 6C. Subtract it. What am I going to get? So this is I think 2C here, and I think this would be minus B plus 2C equal to, तो सही तो आ रहा था. So B is equal to 2C was right, exactly. ठीक है, so B is equal to 2C. Okay, B is equal to 2C was right, and then I can use this up, right? I can use this up somewhere. So if I write B is equal to 2C, I'll get two equations, that is 6C minus 4C equal to 0, and then I will get 3A plus 2C plus C is equal to 0. That implies A is equal to minus of C from here. Okay, A is equal to minus of C, right? A is equal to minus of C I've got. Okay, and now what I can do, okay, so basically what is happening is it will create a certain problem here. Okay, so you can, okay, so I have one thing that is very much clear, that A can be equals to what? A can be minus of C, and B can be equals to what? It can be plus 2C. So from this we can arrive at one result, that is let's say take C is equal to 1. Let's say take C equal to 1. If I take C equal to 1, B will be equals to what? 2. And if B is equal to 2, then A will be equals to what? A will be equals to minus of 1. Right? So one of the values can be this also. One of the values can be this also. One of the values can be this, because if you're going to plug it again back into the equation, then again nothing is going to get, you're going to get C equal to 0. That is not a concern. The concern is that if C is equal to 0, yes indeed, if C is equal to 0, then indeed you will get all these as 0 terms. But understand, even this satisfies this equation, right? So if simultaneously solving all these three, you can have many different non-zero values. You can have many different non-zero values for ABC, right? You will have, okay, let me develop another formalism for you. Non-zero values for ABC. It implies what? It implies that this set is not linearly independent. This set is not linearly independent. Okay, yes, exactly. That is what I was about to tell. Okay, now if you want to simplify this, let's say if I'm saying that what we want, basically, if I'm saying that A times some x1, x2, x3 we want to do, right? Plus B times y1, y2, y3 we want to do, and plus C times z1, z2, z3 we want to do, right? And eventually we want to write it as 0, right? So this, what does it imply? It implies ax1 plus by1 plus cz1 should be equal to 0. It implies ax2 plus by2 plus cz2 equal to 0, and similarly it implies ax3 plus by3 plus cz3 equal to 0. Now if you see, if I have this, if I write it in matrix notation, what I will get? Okay, so eventually this is the this matrix x1 x2 x3, and this I think this is quite clear. Now if I get from this matrix this a equal to 0, b equal to 0, c equal to 0, if I get all of them equal to 0, all of them equal to 0, see, if I get all of them equal to 0, only then it makes sense that my set is my like these sets. Let's say this is x, this is y, and let's say this is z. Only then I can say that x comma y comma z are linearly independent. See, only if I get a trivial solution, only if I get a trivial solution. See, what I want to convey, only if I get a trivial solution, only then I can say now that a is equal to 0, b is equal to 0, and c is equal to 0. Yes or no? Is that clear or not clear? So I'm actually following what Bharat is saying, so that would make your life easy. See, what I want to convey, I'm saying that let's say we have three vectors in R cube. Let's say x1, x2, x3, y1, y2, y3, z1, z2, z3. Let us denote it by x, comma y, and z. If these are linearly independent, then can I not write it in this fashion? And can I not write it in this matrix notation? And if this is invertible, then it is sure that I'm going to get, if it is invertible, then it is sure that the solution would be trivial. If this matrix, this, let's say A, this is comprising of these. So if this particular A matrix is invertible, then this would be fine. And invertibility implies what? Determinant of A should be non-zero. Determinant of A should be non-zero. So if the determinant of A is non-zero, then I will obtain the trivial solution. Also, this can also be one of the ways from where we can judge about linear independence and linear dependence. Let us take one example, and then that would be better to take one example, and let's do, because we have exhausted our example here. Okay, just give me a minute. There is an internet connection problem. Just let me help myself, and I'll give you one example. Okay, so yesterday we discussed I think basis. We did discuss basis, right? And for what are the conditions required for basis? What are the conditions required for basis? For a basis, the first thing is that, let's say if you are saying that these vectors are forming the basis, then are linearly independent, point number one. And second, all these elements generate B. That is, the span of B is nothing but it is equal to the entire vector space V. Is that clear? Yes or no? So for, let's say yesterday we were doing what? Just give me a minute. Yesterday we were saying that basis 1, 0 and 0, 1, they are linearly independent to each other. And we saw today also that they will span the entire R square. So we can write alpha 1, 0 and we can write beta 0, 1. So clearly this will span the entire R square. So this will generate the entire R square. So if this is the set B, a subset of R square, so we can say that B generates entire R square. Also, these two vectors are linearly independent. So this B forms the basis set. So you can say that for R square, these are the bases. Is that clear? So now let us check a basis. And for checking basis also, you're going to check what? You're going to check linear independence. So let us do a few questions indirectly here for the linear independence also. That will actually serve as a exercise for you. Okay, so actually that would be better to use the matrix thing. Okay, so now let us I'm giving you a few questions. Now try to do this. Okay, just verify that which of the following forms the basis for R cube. Okay, just verify which of the following forms the basis for R cube. I'm giving you examples. Just verify this. Okay, this is 1, minus 1, comma 0, comma 0, 1, comma 1, comma 1, and 1, comma 2, comma 3. Do you think that this forms a basis? Do you think that this forms a basis? This forms a basis. So I'll do it in once in the manner which we were doing. See, for basis, the first thing that needs to be checked is whether they are forming linear independent vectors or not. This is first thing that you need to check. So here it is. Let us check. So again, I'm writing only once. Okay, then I'll not write this way. Minus 1, comma 0, comma 0. Then I will write b, comma 1, comma 1 plus c 1, comma 2, comma 3 should be equal to what? It should be 0, comma 0, comma 0. Right? For for linear independence, what one needs to check that a equal to b equal to c is coming or not. Okay, a is equal to b equal to c is coming or not. So I'll write it once minus a. I'm writing minus 1 into a एक बार के लिए. I'm writing minus 1 into a. Then I'm writing 0 into a. Sorry, minus 1 into a. Then I'm writing 1 into b. And then I'm writing 1 into c equal to 0. Then I'm writing 0 into a. This is 1 into b, just to show you that matrix thing. Okay, 2 into c is equal to 0, and then 3 into c is 0 here. I think this is something that you can follow. Okay, this is 1, and I think this is 0 into a. Okay, so what does it imply? It implies that this matrix would be what? This matrix would be simply minus 1, 0, 0, 1, 1, 1, and then you have 1, 2, 3, and then I can write a, b, c. Now, if this particular matrix is invertible, then I will obtain what? Trivial solution. So let us see that whether the determinant, what is determinant of A? So determinant of A would be minus 1, 1, 1, 0, 1, 2, and 0, 1, 3. Try to find the determinant. So this will be, I think, minus 1, minus 1. So minus 1, 0, 0. Okay, so minus 1 is certainly not equal to 0. So we can say that it implies what? It implies minus 1, comma 0, comma 0, 1, comma 1, comma 1, and 1, comma 2, comma 3 form what? Form linearly independent set of vectors. They form linearly independent set of vectors. And it's quite easy to see that if you write this minus alpha plus beta plus gamma, this will be 1, comma beta plus 2 gamma, and then you can write beta plus 3 gamma. Clearly all these things are what they will this will span the entire R cube also, right? This will span the entire R cube as well. You can see this will come from real entries, this is from real entries, and this is from real entries. You take alpha, beta, gamma from real, so eventually this will be R cross R cross R. So it will span the entire R cube. It will span the entire R cube. So clearly they will form the basis. They will form the basis. Is that clear or not? Yes or no? Is that clear? Or should I move to another question? Try to find this. Whether they form bases or not. Whether they form bases or not. Whether they form bases or not. That also we can do. Bharat is right. We can form the matrix of given vectors and perform addition and subtraction to show that yes, that also can be done. Okay, first and third are linearly dependent, right? So this is okay. 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 So what you can do, in order to see this, you can do one thing. You can just go and write this. Okay. So just let us take the matrix 0, 1, 2. Try to take this 1, 1, 1, and you take 1, 2, 3. What would be it? I think this would be 1 and again 1. Minus 1 plus 1. Okay, 1 minus 1. Sorry, 1, 1 minus 1. So 1 minus 1 is 0. So clearly again this will be linearly dependent set. So it will not form. It will not form a basis. Is that clear? One more question let me do, and then we'll move on to some different questions in the same basis ones. Okay, so just keep your concept here clear. Just think about this: minus 1, 1, and 0, 2, comma 0, comma 0, and 0, comma 1, comma 1. Do you think this forms a basis? Just you need to check the determinant, and things will be done for you. Check this: minus 1, sorry, minus 1, 1, and 0, 2, comma 0, comma 0, 0, comma 1, comma 1. Check this. It will be simply minus of 2, sorry, non-zero. So I can say that this will be linearly independent set of vectors. So they will form what? Basis. Is that clear? Is that clear to Siddhi also? Is that clear to everyone till now? I don't think there is an issue. Okay, good. Now try to do this. And I'm giving you another question. I'm giving you another question and a little bit different. Let's see if you are able to do it. Okay, so just a question for you. Let V be a consisting of all the matrices with zero trace and such that the entries of the first row add up to 0. Entries of first row add up to 0. Uh, just write one of the bases. Try to write the basis. Try to write the basis. Okay, thing is that matrices with trace 0 such that the entries of the first row add up to 0. Okay, we want to write the basis for this. Just give me a minute. I'm coming back in a minute. Just try to do this. Okay, so I'll do it for you, don't worry. Okay, so what was the question? Question was we wanted to write, so V is what? V contains, okay, so skip it. Okay, so what does V have? V is the set of all those matrices, okay, of 2 cross 2. So let us take a 2 cross 2 matrix, let us say A, B, C, and D. Okay, let us take, right, that is fine, that is fine. Minus 1, 0. Okay, that would do. Okay, that would do. So A, B, C, D, such that it belongs to what? Obviously, it belongs to real entries. Let me write that all these A, B, C, Ds belong to real. Okay, so these belongs to A, B, C, D belong to real, such that the row of first, the sum of the row elements in the first one is 0, and then trace is 0. So A plus D is also 0. What does it imply? It implies that A plus D is 0. So it implies that A should be equal to minus B, or B is equal to, I should write B is equal to minus A here. And also you can write that A plus D is equal to 0. Then I can write that my D should be equals to minus of A. D should be equals to minus of A. Okay. Now it implies what? That it implies that my V would be nothing but it would be this kind of set. A, what is B? B is minus of A. What is C? C is not identified. Let it be. And D is what? Again minus of A. Okay. So one of the example of basis can be what? So example of basis set for this V would be what? What do you think? What I can do is I can write either 1, minus 1, minus 1, 0, or I can write what? I can write this also, 0, 0, 1 and 0. Okay, if I want to express this matrix, I can use these two vectors or not? I can use these two vectors, right? Let's say this is your V1, let's say this is your vector V2. So if I write V1 plus V2, sorry, A times V1 plus C times V2 equals to this. So I'm getting this, I can generate this. One thing is clear, I can generate my these kind of this particular subspace V with these two, but with these two. Is that clear? Not clear? Am I able to explain you? See what I want to convey. I want to convey that this particular subspace V, which contains the matrices of the type A minus 1 minus A and C, can it not be generated by these two vectors V1 and V2? Should I is that clear or not clear? See, what did I tell you? I told you that the sum of the first row should be 0. The row elements in the first, okay, good, and the trace should be 0. So if this is the case, then these are the matrices that the result is what? A minus and C. What you can do? Can I not write this particular matrix in form of the linear combination of these two? I can write it AV1 plus CV2. Clearly it is clear the case. And what I can do, I can confirm the linear independence by saying that let us compare it by a 0 matrix. So I'll do it. I'll write here 0, 0, 0, 0. And if this is the case, what I'm going to get? I'm going to get C is equal to 0 clearly. If you see here, C is equal to 0, and if C is equal to 0, then certainly A should be equal to 0. So A V1 plus C V2 is equal to 0 implies what? A is equal to 0 and C is equal to 0 implies what? It implies 1, minus 1, 0, minus 1, comma, 0, 0, 1, 0. This set is going to generate my V, that is point number 1. And point number 2, they form linearly independent set of vectors also. They are linearly independent set of vectors. Their linearly independent set of vectors plus they are going to generate V implies what? It implies that these are the basis set. These are the basis set, indeed. I hope it is clear. Okay, now let us do one more question and then we'll do something. I think today's time is done. Okay, so we'll do tomorrow linear transformation. So I thought today we will be able to do linear transformation. Okay, so we'll do tomorrow linear transformation. I think it's enough for today, but let me do a few more questions then. Let us cover a few more questions then. Question is, uh, write down the basis for the write down the basis for the following subspace. For the following subspace. Write down the basis for the following subspace. Okay, and the subspace is V is given to be x comma y comma z comma t belongs to r power 4 and z is equal to x plus y comma x plus y plus t equals to 0. So if you want to write the basis for this particular subspace, how is that possible? How am I going to write it? So I'll do it for you. Don't worry. See, if this is the what you can say, this is the space subspace V. Then you see what you can do. You can write your V. Uh, X and Y, they are fine. You have to write this way only. What would be your Z? Z would be simply X plus Y. And what would be T? T would be simply minus of X plus Y. Okay, and this is such that this entire thing, okay, I'll write this entire is a subset of r power 4. I know that r power 4, r raised power 4, or you can say r4 is a vector space, isn't it? It is a vector space, and clearly this V is a subset of r4. So this is a subspace. This is a subspace. We want to identify the basis for it. So the basis can be what I have to do. Just take some of the things, like let's say take x equal to 1. Let us say take x equal to 1. Let x equal to 0, y equal to 1. So it will give me 1 here and it will give me minus 1 here. So this is 1. Another one can be, let's say take this as 0, take this as 1. This would be 1 and this would be minus 1. So this is the basis for B, isn't it? You can make another basis sets also. I'm not saying that you cannot make. You can make on your own also. You can take x equal to half, y equal to half also. That way also you could do. But you have to check that whether these are linearly independent or not. That is something one needs to check also. I think this should be not. Let us. These are the same now. So let us take this as 1, this as 0. Okay. This has 1 and this has 0. Okay, sorry. So this has 1 and this has 0 and all these things. Okay. So does this form basis for V? Let us check. Let us check that. So clearly this is very much clear. If I write alpha 0 comma 1 comma 1 comma minus 1 and plus beta 1 comma 0 comma 1 comma minus 1, it will yield me what? It will yield me beta comma alpha plus beta and comma minus alpha plus beta. And from this I can generate entire r square, r power 4, because here entries are real, here also entries are real. So basically it corresponds to r cross r cross r cross r. So it will form your entire r power 4. So this will generate your entire r4. Now one needs to check that if alpha plus beta is equal to 0 comma 0 comma 0 comma 0, then what is the result? From here if I compare, it implies beta equal to 0, it implies alpha equal to 0, and if alpha is equal to 0 and beta equal to 0, then alpha plus beta would be 0 and this would be 0. So clearly if I'm taking the linear combination of 0 1 1 minus 1 and 1 0 1 minus 1 and equating it to 0 0 0 0, then alpha is equal to 0 and beta equal to 0. That implies 0 comma 1 comma 1 comma minus 1 and 1 comma 0 comma 1 comma minus 1, they indeed form the basis sets for r power 4. Is that clear? I hope it is clear till now. If that's clear, then I'll the first step. Okay, the first step. Okay. See, what was given to you? It was given to you that z is equal to x plus y. Where did it come from? Okay. See, it was given to you that z is equal to x plus y. So I have written z is equal to x plus y here. And what is t? T is after all related by this equation. So I can write that my t would be simply equals to minus of x plus y. So here I have written instead of t minus of x plus y. Is that clear? I hope it is clear till now. Okay, so now another thing that a few more things you can check on your own. I'm giving you check whether this forms a basis or not for P. That is a set of polynomials. Okay, again this is a polynomial. Okay, whether this forms a basis or not. Okay, question. Think about this: 1, comma x plus 1, comma 3x minus 1, and comma x square. Is it a basis for P2? It is a P2, and you understand the P2 set of all polynomials with degree at most 2. Okay, now you just think that whether this forms a basis for P2 or not. Whether this forms a basis for P2 or not. Okay, so I'm just giving you a quick observation. Okay, at times you have to observe also. Okay, at times you have to observe. Just observe. See, what I can do, I can take this 0 times x square, fine. Okay, forget about this. Just think about these linear terms. Just think about these linear terms. There is a linear term 3x minus 1, so I'm keeping it as it is. Okay, this 3 is there, so what I'll do a subtraction with minus 3 x plus 1. So this will get subtracted. 1 minus 1 is minus 1, minus 3, so it is minus 4, so I'll write plus 4 into 1 equal to 0. So what is happening? Let's say this is your V1, let's say this is your V2, let's say this is your V3, and let us say this is your V4. Okay, now A1 V1 plus A2 V2 plus A3 V3 plus A4 V4 is equal to 0, and not all AIs are 0. Not all AIs are 0. What does it imply? It implies that this set of vectors, that is V1, V2, V3, V4, V1, V2, V3, V4 are what? They are linearly dependent set of vectors. Since they are linearly dependent set of vectors, it violates that they are the basic condition for basis, so it cannot be a basis. Is that clear? It cannot be a basis. Is that clear, Siddhi? See, for a basis for anything to for a subset to be a basis, what is required? The first condition is that that the elements of the basis must be linearly independent, right? But here you can clearly see that these are not linearly dependent. These are linearly dependent rather. So they cannot be the basis. However, if you see these vectors, which I'm going to write, okay, just think about them. Or should I give you an example of something? Okay, let's say this is an example, one of the example which will serve as a motivation. this indeed will form. So I'm writing this will form. Just confirm it. This will form a basis. This will form a basis indeed for P2. P2 is what again? Set of polynomials with degree at most 2. So this is 1, x plus 1, and then you have x square plus 2x. This will form a basis set. Yes, it will form a basis set. Try to find whether this forms a basis set or not. Okay, this I'm leaving it to you to as an exercise, as a homework. Try to do this as a homework. Okay, try to do this as a homework. Okay, so this will indeed form a basis for P2. This is something that I'm leaving up to you to verify yourself. Now, yesterday we also discussed something called as dimension. So let us do let us revise it so that from tomorrow onwards, when we are going to do this thing, linear transformation, then things would be easy for you. What is a dimension? I told you the total the total elements. You can say that what you can say that if there is a set of linearly independent vectors. Okay, if there is a set of linearly independent vectors, you can say the number of those. You can say the number of those. You can say number of elements of basis. I will write uh, in more formal way. Let's say this V forms a vector space over field F, and the basis. Basis after all is what? They are nothing but they are the number of linearly independent set of vectors in which you can span the entire V, right? So number of elements in basis. This forms the dimension. This forms the dimension of V. This forms the dimension of V. And I told you that if there is only a null element, that is 0, and I told you this forms a subspace also. So it is a vector space in its own right. So only for this you will have the dimension as 0. If the vector space does not have a finite basis, then those are called as the infinite dimensional vector spaces. Is that clear till this point? Okay, now just a simple question. What do you think? See, I have already proven that the set of complex number, I'm writing here, set of complex numbers, set of complex numbers form a real vector space. This is something that you know. Set of complex numbers forms a real vector space. Okay. So I know that my set of complex numbers denoted by this is forms a real vector space. What do you think would be dimensions of this? What do you think would be the dimensions of this set? Yeah, number of independent elements. Yes, number of linearly independent elements. That would do. Number of linearly independent elements would do. Okay, so number of elements in the basis set would do. So number of elements in the basis set, they would give you what is called as the dimensions. Is that clear? Okay. So what do you think the dimension of the set of complex numbers would be? See, I told you that in order to generate a complex number, what I can, after all, what is complex number? You can just think it as like r square only, no? So you can have a correspondence to r square, because after all, if I want to write any complex number, let us say if I want to write x plus iota y, here x and y belongs to r, right? X and y both belong to r. Okay. If I want to generate this set, what I can do? I can generate it using 1 comma 0 and 0 comma 1. After all, whether you write x plus iota y or whether you write x comma y, this is one and the same thing, right? If I want to generate this entire set, what I want to write, what I can do? I can just do this. After all, if you want to write x plus iota y, or you write this way, this is one and the same thing. So for every point in the complex number, for every complex number, there is a point on the plane. So how many basis vectors are required? How many basis vectors are required? So number of elements in the basis are what? 2. And this is something that we've already proven. They form the basis. Okay. So number of the elements in basis set is what? 2. So clearly always remember the dimension of this set is equals to what? 2. I hope it is clear. Two. Yes. Okay. Now just think about this. What do you think the dimension of more of such questions we are going to do tomorrow also? So because tomorrow is linear transformations. So actually, I thought today I'll start, but somehow. Okay. What do you think that Pn? What do you think the dimension of Pn would be? What do you think the dimension of Pn would be? Okay, what is Pn? Remember, this Pn is set of polynomials. These are set of polynomials with degree at most n. Okay, so clearly, what would be the basis set? Basis set would be 1, comma, x square, comma, x cube, dash, 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 x power n. You can generate any element from this. This will form your basis. So usually students get confused. They write n. Answer is n plus 1. See this. Don't forget this. This is x raised to power 0. So what would be dimension? Dimension would be n plus 1. I hope it is clear till now. Okay, so I hope I have done a little bit amount of you can say homework for actually getting into linear transformation. A few of the things we are going to see tomorrow also with regards to dimensions, and then we'll begin with the linear transformations, which is again an important aspect for your linear algebra. And then we'll probably take 2 lectures on this linear transformation and probably 2 on inner product spaces, or you can take 1 more. So mostly 4 to 5 lectures will sum up your entire you can say introductory linear algebra. So I hope you will keep patience. I'm again urging you that keep patience, because see, all these things are directly or indirectly going to you're going to directly or indirectly see all these things in your operator theory or things like that. So if you're well versed with all these things, then I don't think there will be an issue there. So that is why I'm requesting you to keep patience, and we'll start very soon the quantum mechanics part also. So till then, I hope you are doing well. I hope to meet you tomorrow. Till then, take care. Bye bye.